A. On how it's made. Suits of armor. Working the night shift. Street light poles. We shed some light on how they're produced. Bent hardwood. We'll visit a factory that doesn't give you the straight goods. Membrane switches. The secret behind those appliance touchpads. If you're the type of guy who finds wearing a tie uncomfortable, try sporting a suit of armor. Armor reached its peak during the battle-filled 15th century. Initially, it was made of chainmail, tiny rings of metal linked together. Then, for greater protection, knights began wearing plate armor, suits made from large pieces of steel. Today, armorers make this obsolete battle gear mostly for historical reenactment buffs. This workshop specializes in custom-made suits of armor. The armorer has to take 45 different measurements just to prepare the pattern. He traces each pattern piece on a steel sheet that's about 1.5 millimeters thick. Then he cuts along the trace line with a bandsaw. This is the breastplate, which covers the chest and abdomen. Now he begins to shape the piece using an automatic hammer. There's no mold or template to guide him. He works strictly by eye. Now that he has the basic shape, he refines it using a manual hammer. He strikes the metal against an upright log, a bag of lead beads cushioning the blows. This prevents the metal from deforming. A few lighter blows without cushioning in select spots to finalize the shape. Until now, he's been hammering the inside of the breastplate. Now he works the outside. He smooths the metal surface, a process known as planishing. Now, using a different automatic hammerhead, he stretches out the breastplate's bottom edge to form a rim angling outward. He places the piece on an anvil, then using a manual hammer, planishes the rim. When you wear this heavy metal breastplate, the rim takes some of the weight off your shoulders by distributing it over your hips. The armorer checks the shape, then makes any necessary adjustments. Now, using several different hammers again, he works his way around the rest of the breastplate, gradually rolling the edge onto itself to form a rounded lip. Rolling the metal onto itself to form the lip reinforces the perimeter of the breastplate, and the rounded edge prevents the sharp metal from cutting the skin. The breastplate is now ready for the finishing touches. First, the armorer smooths the surface with medium grit sandpaper, then with fine grit sandpaper, then the last step with fine grit paper and a polishing compound. Some breastplates have an articulated styling. For this model, the armorer uses 3 brass rivets to attach the sections. He fastens them loosely to enable the pieces to move. Then, using rivets again, he attaches leather straps. A suit of armor is made up of about 20 different components, such as the front and back shin guards, called greaves, armor and leather gloves, called gauntlets, shoulder pieces, called pauldrons, and of course, the helmet and visor. A knight would don his suit of armor from the bottom up. Otherwise, the weight of the top components would have him keeling over half-dressed. In the Middle Ages, a suit of armor cost as much as a small farm. It was a prized luxury only the nobility could afford. Being a modern-day knight in shining armor doesn't come cheap either. A base model suit costs about $3,000. An elaborate one, up to $20,000. We take well-lit streets for granted, but there was a time when venturing out at night meant traveling in complete darkness. In 1814, the first gas lights lit up the streets of London, England. The first electric streetlights illuminated a public square in Cleveland in the United States in 1879. These streetlight poles are made of what's called composite, a combination of fiberglass and epoxy resin. Epoxy resin is a gooey liquid plastic mixed with a hardener. The factory constructs each pole on a mandrel, a long tapered metal cylinder. Workers first lubricate the surface. Then they take what's called fiberglass filament, a string composed of 2,200 tiny fiberglass strands. They'll wind dozens of filaments around the mandrel to create the pole. But first, the filaments go through a bath of epoxy resin. This resin is moldable, and once it's heat cured, maintains its shape. Once the filaments come out of the bath, a machine called a filament winder wraps them around the rotating mandrel. The speed of rotation in relation to the speed of the winder is critical because it dictates the angle of the fibers. The lower the angle, the more that part of the pole will be able to withstand the wind and provide constant, stable lighting. When a pole bends in the wind, the light appears to flicker. The number of filament layers depends on the design of each specific pole, and that's determined by a couple of factors. First, the type of light fixture the pole will hold. The bigger the fixture, the stiffer the pole has to be. The other factor is wind. The windier the location, the stronger the pole has to be. Once the winding's done, the mandrel moves on to the curing station. They pump pressurized steam into the hollow inside of the mandrel. The heat kickstarts the hardener and the epoxy resin. This solidifies the resin and cures it. The mandrel rotates so that the pole cures evenly. Curing time depends on the length of the pole and how many filaments it's made of. To help extract the pole, they pump cold water through the mandrel. This makes the steel mandrel contract, loosening the pole. Remember how workers lubricated the surface of the mandrel before winding the filaments? Because of that, the pole just slides off. The pole now moves on to the finishing stages. First, an automated sander works the surface. The customer can order from a choice of surface textures, from smooth to rough. Sanding takes just a few minutes. Now a saw makes a neat cut at the top of the pole where the metal tenon will go. A tenon is the component that'll hold the light fixture to the pole. This particular model has an arched mounting arm. The composite has cooled a bit since curing, so they reheat it to make it flexible. After a bending machine makes the curve, they spray cold water inside to cool the material. This registers the curve in the resin's memory, setting the bent shape. Now they cut out the hand hole, the opening through which the electrician will connect the underground wire to the fixture wiring. Workers then spray the pole with urethane paint. The paint acts like sunscreen, protecting the composite from damaging ultraviolet rays. This grommet hole will connect to the underground pipe that contains the electrical wires. After installing a cover over the handhole, it's time to assemble the parts. The underground pipe to the pole, and the pole to the tenon and light fixture. Many products have rounded components made of solid hardwood. Often the companies that make these products hire factories that specialize in wood bending to prepare these components for them. Bending wood may sound simple, but it isn't. It takes a lot of preparation and skill to bend wood without cracking it. The best type of wood to bend is hardwood. Its fibers react better to heat and moisture than softwood fibers do and therefore curve nicely. If you bend softwood, it wrinkles. The wood first goes into an outdoor dryer to bring its humidity level down to between 15 and 20%. This prevents the wood from expanding and contracting after it's bent. This air drying process takes up to a week. Once the wood is dry, a powerful trimmer saws the pieces to the required length, an edger to the required width. Now that the wood pieces are the right dimensions, they go into what's called a steaming box. This superficially rehumidifies them so that they become somewhat flexible. This takes from 10 to 45 minutes depending on the type of wood and its thickness. This humidity will later evaporate out of the wood. Now the pieces go into a press sandwiched between two forms in the shape of the curve to be made. The press applies both pressure and heat. Pressure to bend the wood. Heat generated by a high-voltage electric current to cure it, setting the new shape. How long the pieces stay in the press depends again on the species and dimensions. Generally, it takes from 20 minutes to an hour. Making this particular type of curve is called crown bending. Workers measure each piece against the template to ensure the curve is just right. The factory uses the same process to bend these pieces into a different shape. It's critical to use just the right amount of heat and pressure. Too high a temperature would burn the wood. Too much force would crack it. These straight pieces of wood will become the rounded backs of Windsor-style chairs, which is why this type of bending is called Windsor bending. Workers humidify the wood in the steaming box, but will shape the pieces using a pressure-only process. They mount what's called a bending mold onto a hydraulic press. This machine uses just pressure to bend the wood around the mold. No heat this time to immediately set the shape. Instead, once the press curves the pieces, workers hook up a chain to temporarily hold the shape. Then they transfer the bent pieces to a heated indoor dryer. The drying process takes between 2 days and 2 weeks, depending as before on the type of wood and the dimensions. Once the wood dries out, the curve is permanent. There are many wooden products that require bent components. This wheel for a horse-drawn carriage, for example. Back to the Windsor chairs now. A dowel machine rounds off the bent pieces. Before shipping the pieces out, workers run them through a sander. This prepares them for the furniture factories who'll varnish or stain and varnish them. Upon receiving these chair backs, the furniture factories will assemble them to the straight parts of the Windsor chairs. The term membrane switches probably means nothing to you, but chances are you use them or at least see them in use daily. Membrane switches are those soft touchpad buttons on the controls of many electrical and electronic devices. For example, the buttons on a microwave oven or on a cash register. The surface on the appliance's control panel is called the graphic overlay. It's a sheet of plastic on which they print the design of the control buttons. Each button has a membrane switch underneath it. To make this graphic overlay, they first laser print a sheet of acetate film with the design, as many copies as will fit. They lay the film on a polyester screen coated with a light-sensitive chemical. Then, using this machine, they expose the screen to 2,000 watts of ultraviolet light for up to 6 minutes. The light hardens the chemical on the parts of the screen that aren't shielded by the design on acetate. This blocks the screen's minute holes everywhere except in the design. Workers remove the acetate film and rinse off the shielded chemical that didn't harden. Now they have a screen stencil of the design they're going to print. Workers dry off the screen and install it on a printing press. A squeegee drags the ink across the screen, pushing it down through the open holes, printing the design onto the overlay plastic. Ultraviolet lamps cure the ink in a matter of seconds. Each color of the design goes on separately. That means that there isn't one printing screen for the entire graphic overlay, but rather a separate screen for each color. Meanwhile, on another screen printing press, they print the circuitry layout onto transparent plastic. The ink contains silver, which conducts electricity. The circuitry layout will go behind the graphic overlay. Again, they print several at a time. Once the printing's done, it's time to assemble the layers that make up the membrane switch. First, the circuit layer goes onto an adhesive sheet. A roller ensures a solid, airtight bond. This spacer sheet will separate the overlay and circuit layer to prevent contact between the two from being continuous. Over each circuit goes a dome made of nickel-plated stainless steel. This forms an electrical contact over the circuit that must be forcibly pressed in order to activate the circuit. They adhere a polyester sheet to hold the domes in place for now. After cutting out each circuitry layout and each graphic overlay, they expose the adhesive backing on the overlay and stick it to the circuit layer. The membrane switches are now complete. This control panel is for a hospital bed. Some membrane switches have a light-emitting diode, or LED, a tiny colored light that goes on when you press the switch to confirm contact. The factory's robotic machines deposit 2 drops of epoxy paste on the circuit layer wherever an LED will go. The paste contains silver, again to conduct the current. A robot then picks up the LEDs and deposits them on the drops of paste. The robot then puts a dome on each circuit, creating an electrical contact. The red light you see is a camera checking the positioning. Testing equipment runs a current through the circuitry to make sure that everything works. Then a drop of transparent sealant goes over each LED. The sealant hardens under ultraviolet light, holding everything solidly in place. Now workers remove the panel from the automated line and plug it in. Lighting up all the LEDs helps them position the graphic overlay properly. This control panel is for a wall oven. No LEDs on this model. And instead of a dome behind each button, they print an electrical contact using the same conductive silver ink they use to print all the circuitry. After rolling on the graphic overlay, they peel off the protective plastic, then flip the control panel upside down and snap it into its cover.
Today, on how it's made. Three-wheeled vehicles. What you get when you cross a race car and a tricycle. Baseball bats. We'll cover all the bases to bring you this story. Artificial bonsais. How to fake a centuries-old botanical art. And trombones. We'll tell you all about the brass tactics. Three-wheeled vehicles were introduced in the 1990s as exotic concept vehicles. This one is like a motorcycle on steroids. It has what's called a reverse trike design, 2 wheels in front and 1 in the back. It hugs the road like a race car, yet is legal to drive through city streets. This vehicle goes from 0 to 100 kilometers per hour in just 4.1 seconds. No faster than a motorcycle, but it definitely turns heads. Production begins with 34 steel tube components that will form the vehicle's chassis. A worker places them in an assembly jig. This positions the tubes for welding. After clamping the components in place, it takes the worker about 4 hours to weld 68 different areas together. For efficiency, 13 of the larger, more complex structures are pre-assembled. The steel tubes measure 3.8 centimeters in diameter, but the metal itself is only 1.5 millimeters thick. They're like those used in the aviation industry, strong yet lightweight. This company uses a visual reference method to assemble smaller parts of the vehicle. Before starting, a worker places 80 components on a board with labels that identify them. This way, he's certain he won't forget any nuts, bolts, bearings, brackets, or horns. Using an electric crane, a worker hoists the vehicle's 4-cylinder, 152 horsepower, 1200cc motorcycle engine into the chassis, now tinted black. Using a pneumatic wrench, he attaches it with 6 bolts and 6 nuts. Here, a worker assembles the 50 parts that make up what's called the footbox. This includes aluminum clutch, brake, and gas pedals. The brake pedal is thicker to withstand more aggressive use. The vehicle decelerates from 100 kilometers an hour to 0 in just less than 29 meters. He coats part of the brake pedal with a liquid sealant so vibrations won't loosen it. Another worker then mounts 2 output hoses and 2 plastic reservoirs for brake fluid. The brake fluid must withstand heat of 343 degrees Celsius, 30 degrees hotter than what's required for most cars. This enables better engine performance. He installs the footbox onto the front of the chassis using 3 bolts. Controlling the speed with the footbox is crucial, since top speed for the vehicle is 230 kilometers an hour. Next, he installs part of the suspension system, a cylindrical gas shock absorber. This attaches to the brake system, which is a zinc-plated rotor and an aluminum caliper. Then they attach what's called the 4-into-1 exhaust manifold. The 4 pipes merge into one to vent the exhaust fumes from the engine. They install the electric fan and radiator assembly. Next, a worker attaches a removable leather-covered aluminum driving wheel to the steering column. The driving wheel locks into place with a spring-loaded latch system. Just like a race car, you attach the steering wheel after you sit in the driver's seat so that you can get inside the vehicle. The collapsible steering column is part of the instrument cluster. This includes dials showing the vehicle's speed, mileage, and fuel. There are also switches for turning signals, hazard flashers, high and low beam lights, and to start and kill the engine. Next, workers install the rear wheel to another part of the suspension, called a swing arm. They attach it with one bolt that's nearly half a meter long and two smaller bolts. Workers then install a chain on the rear wheel assembly. When the vehicle's running, the chain's 94 links revolve on two sprockets to make the wheel turn. Rubber O-rings on each link prevent dust from damaging the chain. Finally, workers attach 19 molded fiberglass body parts. This factory offers 6 standard colors and several custom colors. When assembled, the vehicle is nearly 3.5 meters long, almost 2 meters wide, and just over a meter high. If you have a motorcycle license and a spare $50,000, you too can burn the pavement on this mean set of wheels. If you think a baseball bat is a pretty simple thing, well, you're out in left field. Making a bat means balancing things like weight and thickness. The material it's made of can make a difference. Metal bats hit the ball faster. However, the pros use wood bats because of league regulations, and even the type of wood might impact the score. Barry Bonds cracked a home run record in 2001 with a wood bat like this, one made of maple, instead of the usual white ash. They can never tell just by looking at it that a chunk of maple has what it takes to make a good bat. So they weigh it to make sure the wood is really as thick and heavy as it appears. Next, pointed prongs grip the wood and spin it, while a carbide cutter rounds it. This is a very modern lathe called an XY machine. The rounded blank goes into a room called the library, joining others on the shelf that are waiting for their chance at the big leagues. A worker selects one of the blanks to fill an order that specifies a certain model and size. He weighs it again to make sure it measures up to what the player has ordered. The blank goes onto the XY machine and spins. A computer guides the cutter as it moves on rails and carves into the blank. It whittles 2.5 centimeters of wood from the blank in order to form a handle. It takes a total of 3 passes on this cutter to make the rough shape of a baseball bat, but it's quick work, completed in just 3 minutes. Now it's time for another weighing in. The bat is substantially lighter, which is what they want. Next, he measures the end of a completed bat with a caliper. Using a square-edged scraper, he rounds the knob as the bat spins on a more traditional lathe. He measures as he cuts. With another caliper, he checks the thickness of a completed bat and compares it to the one he's just carved. Now he takes a turning tool called a skew chisel. With its pointed tip, he cuts into the bat's handle just above the knob to narrow the shoulder. Again, he measures as he cuts to make sure the diameter is just right. Using the skew chisel, he shapes the slope of the bat, repeatedly checking with the caliper to make sure it meets specifications. He slims down the handle a little more. Then he angles the top of the knob with the chisel. He shapes the rest of it with a square-end chisel. Next, he curves the bat's barrel using the same tool. This gets rid of sharp edges that would cause a ball's impact to ripple down and jar the player. Then he goes back to the knob and completes the shaping with the skew-end chisel. Because the tool is extremely sharp, he can carve very precisely. The bat is now within 14 grams of its final weight. Using an electric sander, he smooths down some of the rough edges. He switches to a finer grit to finish off the job. As he sands, he measures, because this isn't just about getting the surface smooth. The bat has to be exactly the right size and weight for the player it's being made for. Now he places the bat's knob in an end mill. A spinning carbide disc cuts around the holes made by the pointed grippers on the lathes, producing a gentle scoop. Next, a bigger disc carves into the barrel, cupping it. Some players prefer a cupped bat because it balances differently. Now he places the bat on the scale for the final weighing, and it's exactly what the player ordered. He brushes paint onto the barrel and rubs stain into the lower half of the bat. He presses decals onto the bat so it sports both the brand name and distributor. Then he stamps the model number in gold ink and tops everything off with a light coat of varnish. Now this maple bat is ready for the big leagues and some heavy hitting. Bonsai is a Japanese word that means plant in a pot. Growing trees in pots is a revered art that actually began in China more than 2,000 years ago. During the past century, creating artificial trees known as bonsai zoke has evolved into a hobby with global appeal. Whether it's rustic pine, flowering cherry, or Chinese elm, bonsai zoke can be made to resemble a variety of trees. Some include stones and small statues, a Chinese tradition known as penjing. A craftsman starts by wrapping 13 strands of wire with stretchy, sticky tape used by florists. He uses 13, partly out of respect for a traditional Asian preference for odd numbers. Later, these wires will form parts of the trunk and branches. He wraps the wires with strips of paper towel for thickness and flexibility. To hold the paper towel in place, he wraps the ends of the wires with more floral tape. He then separates clumps of plastic pine needles from their branches. Ironically, this fake vegetation is imported from China. Next, he snips off the ends of the branches, creating segments about 2.5 centimeters long. To reinforce and support these segments, he wraps them with tiny wire that's 0.5 millimeter in diameter. Next, he wraps the segments with floral tape to give them a more natural, branch-like appearance. Then he inserts these segments into the pine needle clumps. The thicker end becomes the bud and holds the clump on the segment. The craftsman now places 3 of these leafy segments together and attaches them with wire. He bends them sideways in the same direction. This mimics the tendency of natural branches to lean towards the sun. For more mature-looking buds, he uses different 3-headed artificial segments. For integrity, 2 different types of buds are never used on the same tree. To add character, the craftsman uses a piece of weathered driftwood as the base of the trunk. He anchors the long wrapped wires into styrofoam around the bottom of the base. He staples the wires to the driftwood and wraps floral tape around the wires surrounding the base. Then he twists the wire to form a sinuous shape, what the Japanese call moyogi. He covers the trunk with soft gray modeling clay, adhering closely to the shape of the driftwood underneath. This will later be covered by artificial bark and moss. This process can take several hours, just part of the 4 to 6 days it takes one worker to make a bonsai zoke. The craftsman then applies slow-drying glue to one side of strips of rice paper. The strips are 5 centimeters long and 2.5 centimeters wide. He uses about 50 to cover the trunk, like bark on a tree. He dabs them with a wet rag so that the creases will remain when the glue dries. The creases make the bark look realistically aged, one of the hallmarks of a good bonsai zoke. Craftsmen are careful to place the branches in the traditional triangle shape. The lower branches must droop, as if weighed down by the elements. They add the leafy segments to the ends of the wire branches, attaching them with wire and floral tape. Using a knife, the craftsman trims away the excess styrofoam around the tree trunk. He then places the tree into an argile pot that's 22 centimeters in diameter and 5 centimeters high. Using a sculpting tool, he covers the styrofoam in the pot with brown modeling clay. Using slow-drying glue, he covers the clay in several shades of fake moss. They range in color from dark brown to light green. He doesn't let the glue dry between each layer because the blending of moss and glue ensures a more natural-looking ground cover. He gently blows on the moss to scatter it across the base. He also applies glue further up the trunk, adhering moss that's thicker and lighter in color to resemble lichen. The finished bonsai zoke is 45 centimeters high. It needs none of the constant care required by its natural twin. Depending on their size and complexity, artificial bonsais range in price from $50 to $800. The adage, "It's hard to improve on a good thing," certainly applies to the trombone. The modern trombone isn't really much different from its medieval predecessor, known as the sackbut, with its distinctive S-shape, hand slide, and bell section. It's a blast from the past, and a pretty loud one, but it can also sound smooth and mellow. The trombone literally slides down to the low notes. It's the only instrument with a hand slide to lengthen it in order to change pitch. To make a trombone, they cut sheet brass in the pattern of a bell stem. They shape it by wrapping it around a steel rod. Using a nylon-headed mallet, the worker hammers the brass to shape it further. It takes just a few minutes for him to hammer out a rough bell stem form. He spreads open the stems slightly so he can make small notches on one edge with snippers. Then, with a brass-headed hammer, he taps down the notches so they hold the edges together. With an acetylene torch, he joins the notched seam, melting in a brass alloy wire to bond it securely. But the seam overlaps, and it's too thick, so he runs it through a seam roller. 2 tons of pressure thins it. But now, the bell stem is too flat. To round it out, he shoves it onto a bell-shaped rod and hammers it back into shape. Then he irons out the hammer marks with rollers. The bell stem, fitting loosely on a steel mandrel, goes through a draw bench. A hydraulic cylinder pushes it through a thick lead washer, pressing it tightly around the mandrel to its shape. To make the bell flare to attach to the stem, he puts a brass disc on a spinning lathe. Using pliers, he turns the edges of the disc to prevent it from flapping while spinning. With a lever, he manipulates a scissors spinning tool, pressing it against the turning brass disc. This shapes the disc into a flare. Making a trombone flare is a delicate business and is the work of a skilled craftsman. Getting it right is critical because the shape will affect the tone of the trombone. Next, with a torch, he braises the flare to the bell stem. The bell stem and flare now turn on a mandrel, while he presses against the seam with a wooden tool. This flattens the seam and gives the bell its final shape. Now it's time to make the tubing. A hydraulic cylinder pulls it on a mandrel through a die, stretching it considerably. In this way, both the diameter and thickness of the tubing are precisely controlled. Then, they become ice tubes, after they're filled with water and put in the freezer. The ice will keep the thin tubing from buckling in the next process. With a lever, he bends the tube around a U-shaped block. As he works it into a U-shape, the tubing hardens. After the ice melts, he places the U-bend in a balling out die. He lubricates the tubing with oil and places a steel ball at the top of the tube and presses it down. He drops in smaller balls and they push the first larger ball through the U-tube. This stretches the inside of the tube, rounding it to the correct diameter, and then the balls exit at the other end. Now he pieces the tubes together and solders them the same way a plumber joins copper tubing. He adds a loop for the valve section. In total, a bass trombone has 2 3/4 meters of tubing. Straightened, that's enough to reach from the floor to the ceiling. But of course, trombone makers are more interested in musical highs and lows. Finally, he solders a brace into place to add structural strength to one of the loops. A diamond-tipped tool engraves the company logo onto the trombone's bell stem, and a cloth buffing wheel spins against the trombone flare to polish it. This custom trombone has been built in approximately 50 hours, something worth blowing a horn about.
Today on How It's Made. Electric baseboard heaters. Nothing but the warm, hard facts. Molded pulp containers. This ain't pulp fiction. Prepared chicken. Passing the buck. And video games. Warning, this report contains graphic scenes. Electric baseboard heaters are inexpensive, easy to install, and practically maintenance-free. Unlike radiators, they're inconspicuous, and they take up very little space. And best of all, you can control the temperature room by room. A baseboard heater is simply wires and a heating element in a steel casing. They make the element using a strip of paper-thin aluminum, 19 centimeters wide. It's lubricated with soap, then goes through a forming machine. A die punches the strip into little squares called fins. They measure 16 by 20 millimeters each and have a circle in the middle. The machine pierces the circles and cuts the fins apart. This machine churns out 600 fins per minute. It stacks them on steel tubes, the lengths of which vary according to the length of the heater. As each tube fills to capacity, a worker takes it away to be wired up. Elsewhere in the factory, meanwhile, they make the heater's casing, using what's known as cold-rolled steel, a flexible type of steel that can be worked without using heat. After a squirt of oil for lubrication, the first die cuts holes for attaching the baseboard to the wall. Then the second die cuts holes for attaching the heating element to the casing. Now the steel travels through what's called the roll former, a machine whose series of rollers successively bend the flat strip of metal, one fold at a time, into the shape of the casing. From start to finish, 20 rollers make 20 bends. The process takes exactly 146 seconds per casing. After the last fold, a computer-controlled die cuts the casing to the required length. The higher the heater's wattage, the longer the casing has to be. Models range from 300 watts, about half a meter long, to 2,500 watts, almost 2.5 meters long. Next, they put a steel junction box on each end of the casing. These hold the wires that the electrician connects to the house wiring. Workers spot weld both junction boxes simultaneously. After a thorough washing, computer-controlled sprayers coat the casings in paint powder. Then it's into an oven for about 20 minutes at 185 degrees Celsius. This transforms the powder to liquid, drying it instantly. After running a red wire for the electrical current the length of the casing, they rig up what's called a linear high-limit temperature control, a safety device that prevents the unit from overheating and catching fire. Gas inside the temperature control expands under intense heat, triggering the device to cut the current. Now they install supports to hold the heating element in place. They're made of satin coat steel, a rust-resistant metal. As the element heats up, it naturally expands. To prevent it from scratching against the metal casing and making annoying noises, they install a heat-resistant plastic bushing. Now they connect the red wire that'll carry the electrical current to the heating element's black wire, capping it with a wire connector. They clip it to the cover of the junction box, easy access for the electrician installing the baseboard. Then they close the junction box cover. At the other end, they connect the red wire and the black wire to the temperature control wire. This runs the electrical current through the safety device at all times. After a voltage test, they close her up and snap on a panel to cover the element. Being toasty warm is now just an installation away. Molded pulp isn't exactly a household word, but it is a household item. Chances are you've got an egg carton in your fridge that's made of it. This thick cardboard-like material can be shaped into a variety of containers, such as those drink carriers they give you at the fast food restaurants. Farms ship out their eggs in trays called filler flats. These flats begin as recycled paper. Old phone books, newspapers, magazines, cardboard, pretty well any product made of paper fibers. The factory even recycles its own flats that have been rejected by quality control. The raw materials go into what's called the pulper, a giant blender that mashes everything up and blends it with hot water that's 43 to 65 degrees Celsius. The hot water swells the fibers, causing them to break apart. After 20 minutes, they become pulp, a watery mixture roughly the consistency of hot oatmeal. The pulp exits out the bottom of the pulper through a filter that screens out plastics and other contaminants. Shaping the flats is a fully automated process. Formation molds descend into a vat filled with pulp. A vacuum sucks the mushy mixture onto them. Water jets rinse off the excess. Rotating above are transfer molds. They grab the flats off the formation molds and move them onto a conveyor. Before the transfer molds grab the flats, though, a brush applies a water-based lubricant. This ensures the flats won't stick to the molds. It's just like greasing a baking pan. The molds themselves are made of bronze, plastic, or aluminum, depending on how long the factory intends to use them. They're covered with a stainless steel mesh. This mesh ensures an even vacuum through the mold so that the pulp spreads over it evenly. The soggy flats now go into an oven for 12 minutes to dry out. The 205 degrees Celsius heat evaporates the water. This bonds the fibers together, forming a rigid material. After they exit the oven, a device appropriately called an upender flips them up so that they stack into each other. A built-in counting mechanism triggers the machine to section off the required number of flats per package, then compress them and seal them in plastic film to keep the dust out. factory uses the identical molding process to make 4-cup drink carriers. These too go into an oven to dry out the pulp, but only for 6 minutes, half the time the filler flats need, because this product is smaller and lighter. Automated compactors stack the finished drink carriers. Then workers compress them for packing and shipping. The factory also makes disposable urinal bottles for hospitals. They add chemicals to the pulp to make the bottles liquid tight. These molds are 3-dimensional and lined with mesh on the inside. When they submerge into the pulp vat, a vacuum sucks in the pulp. When they resurface, water jets rinse the excess pulp off the bottlenecks, and the vacuum sucks out the water. A spiked conveyor belt transports the bottles to the drying oven. They dry at a lower temperature than the flats and drink carriers do, 176 degrees Celsius, and for a longer time, a half hour. This ensures the chemicals making the bottles liquid tight cure thoroughly. While urinal bottles can't be recycled for sanitary reasons, drink holders and filler flats are recyclable, making them extremely environmentally friendly. In the year 2001, Canadians ate 31 kilograms of chicken per person. Given that rate of consumption, if we had to process the poultry ourselves, chances are we'd be in a rather foul mood by dinner. Thank goodness for chicken processing plants. The chickens arrive at the factory with their feet, legs, and heads already cut off. What's left are the breasts and wings. The slaughterhouse also removed the internal organs. A conveyor belt transports the chickens to the cutting and deboning zone, a bustling assembly line operation. Workers prop each chicken on a cone-shaped stand in order to have both hands free to work on it. Cutting up a chicken properly isn't as easy as you might think. The workers get special training. It's crucial they keep their knives well sharpened and wipe them after every 5 or so chickens. The first cuts remove the wings, starting on one side and positioning the knife horizontally in line with the top of the cone. The worker makes an incision where the wing joins the shoulder, then cuts downward across the back of the chicken. Then a quick cut and twist to detach the wing. It's the same procedure on the other wing. The incisions at the wing-shoulder joint must slice through the tendon completely. Otherwise, detaching the wing is difficult. And struggling with a slippery wing while holding a knife in your hand can result in serious injury. The next cuts remove the skin and breasts. They peel off the skin, then pull on the 2 breasts and make a quick incision to release them. They slice the breasts apart, carefully checking for bones that might have broken off from the carcass and be hiding in the meat. The next cuts remove the tenders, the meat located under the breasts. Workers make an incision in the middle just under the wishbone and down the length of the carcass. This detaches the tenders, enabling the next worker on the line to pull them off. Meanwhile, waiting in the wings are the wings. Workers load them onto a machine appropriately called the wing cutter, a mini Ferris wheel that takes the wings for a little ride, right into a sharp knife that chops them into 3 sections: the drumette, the chubby part with the most meat, the winglet, the middle part, and the wing tip, the pointy part with barely any meat. This factory transforms the meatier drumettes and winglets into frozen, ready-to-eat chicken wings. The first step in that process is seasoning. Workers load the pieces into a giant drum. As the drum rotates, they inject the seasoning, barbecue or honey garlic, for instance. After about an hour, the chicken wings come out evenly coated. Now these freshly seasoned wings go into a gas-fired oven where they bake at approximately 250 degrees Celsius for 8 to 11 minutes. They come out fully cooked and ready to eat. They go into a freezing mechanism for about a half hour, then to the automated packaging department where they're sealed in a bag. These chicken pieces, wings, tenders, and breasts, are prepared differently. After seasoning, they travel through a rotating drum that coats them in a flour and breadcrumb mixture, then into a second drum for a second coat. Next stop, a 40-second deep fry in canola oil, just long enough to adhere the coating. Then from the frying pan into the fire, as they say. Well, into the oven, actually. After 20 minutes at about 250 degrees Celsius, these chicken pieces are fully cooked and ready to be frozen and packaged. They started out a generation ago as simple black and white ping pong games on a TV screen. Today's video games are vivid, sophisticated, and fast-moving, driven by state-of-the-art computer software featuring the latest in high-tech graphics. It all started in 1952 with a Cambridge University PhD thesis on human-computer interaction. The student invented a primitive tic-tac-toe game on a vacuum tube computer, the very first computer game with graphics. A team at MIT designed the first recognized computer game in 1962. Then, in 1972, a Stanford student invented the arcade game Pong, which later became a home video game to play on your TV set. It all begins with the people who form what's called the core team. They brainstorm in meeting after meeting to hammer out the concept, how the game will look, how it'll work. Then they plan out the production schedule, assigning who'll do what, when. They break down the game on paper and color code the components. Then they post them on a bulletin board that'll act as the production's nerve center. Now work on the artistic concept begins. Artists sketch out the characters and backgrounds on paper in a scene-by-scene storyboard. Meanwhile, graphic artists recreate those storyboard drawings three-dimensionally on the computer. This step enables the development team to use the latest in computer animation technology to bring the game elements to life by adding colors, textures, shading, and, of course, movement. After developing a preliminary version of each character, the animators superimpose a skeleton. By manipulating the skeleton, they make the character move. They experiment with different movements until they decide on which ones they'll use for the game. The animators have to design every movement each character can potentially make in the game. That's 700 movements for this main character alone. Once that's done, they flesh out the character's features and costumes to completion. The evolution of the characters from the first pencil drawing to the final version is quite remarkable. Other animators work on the backgrounds, the game's playing field. Once they have a rough version laid out, they refine it by adding details, colors, and textures. To give it depth and dimension, they use virtual lighting to create shading and shadows. To advance the storyline, this particular video game is interspersed with 1-minute animated movies. These segments, called cinematics, are animated in high resolution to produce a top-quality image. The interactive game, on the other hand, is in low resolution because computers can't process high-res images quickly enough for fast-moving play. So the animators have to create every character twice in both high and low resolution. Meanwhile, for the cinematics, they animate the storyboard using rough draft characters. This is simply to calculate the timing and to map out a clear path across the backgrounds so that the characters don't collide with the scenery. To make the cinematics action look realistic, they use a technique called motion capture. The animators videotape themselves performing the action, then use animation software to reproduce it on the computer. Computer programmers create the video game's menu settings, among other features. Computer engineers design the artificial intelligence, the brain that runs the game. It's made up of thousands of computer codes. For the cinematics, actors record the characters' lines in a sound studio. An audio technician mixes the voices with music and sound effects and synchronizes everything with the action. Now they take the video game out for a test drive. Do the characters move the way they're supposed to? Do they go where they're supposed to? Or do they run into trees and walk through walls? This is the development team's last chance to rid the game of any bugs. After that, the company can finally market this video game and hope it becomes a hit.